Welcome to Ask and Learn.
In this problem, we have hydrogen gas in a rigid tank which is cooled until its temperature drops to 300 Kelvin. We wish to determine the final pressure in the tank and the amount of heat transfer. We can assume that one, hydrogen is an ideal gas. The tank is stationary and thus kinetic and potential energy changes are negligible. And we can then write down our gas constant for hydrogen, which is 4.12 kilopascal meter cubed per kg Kelvin, and the constant volume specific heat of hydrogen at an average temperature of 450 Kelvin is 10.377 kilojoule per kg Kelvin. Now these are from our tables. So the first thing we want to do in part A is find the final pressure of the hydrogen. And we can get this from the ideal gas relation P1V over T1 is equal to P2V over T2. So if you rearrange this equation, we can make P2 the subject of the formula. So this is P2 is the ratio of the temperatures T2 over T1 times P1. And we can substitute our values into this equation. So that's 350 Kelvin over the initial temperature of 550 Kelvin times the initial pressure of 250 kilopascals. And so we reach a final pressure of 159.1 kilopascals. So that's the final pressure of the hydrogen. Now for part B, we can take the hydrogen in the tank as the system, and the system is closed since no mass enters or leaves. We can write the energy balance equation, which is En minus the energy out. E out is equal to the change in energy of the system, delta E. So this has contributing factors of the heat which is leaving the system. So we have minus Q, since it's heat out, minus Q out, and this is equal to a change in internal energy of the hydrogen gas. And so Q out is equal to minus delta U. We multiply both sides by -1, and this is equal to minus M into U2 minus U1, the specific internal energies. And this can be written as M times the heat capacity CV at constant volume into the temperature T1 minus T2. So again, we multiply it by -1, and we replace U2 by CVT2 and U1 by CVT1. Now that we have the energy balance equation, we can find, firstly, the mass of the gas. So M is equal to P1V over R T1. And this is equal to 250 kilopascals times a volume of 3 cubic meters all over R for hydrogen is 4.124 kilopascal meter cubed per kg Kelvin times T1, which is 550 Kelvin. And so we get the mass of the hydrogen gas to be 0.3307 kg. So now that we have the mass of the hydrogen gas, we can go back and substitute this into the energy balance equation, and we can find the heat transfer. So the heat transfer Q out is equal to the mass 0.3307. We'll suppress the units here into 10.377 into a change in temperature of 550 minus 350, and that's in Kelvin, and hence we get the heat transfer to be 686.2 kilojoules.